All right, class, we've arrived at section 5.6, rational functions. So a rational function is a function that can be written as a quotient of two polynomials, polynomial p of x and q of x. And so this is what I really want you to remember of a rational function. I know that this can look scary, but basically we have just a polynomial on the top over a polynomial on the bottom. We obviously want q not to be 0 because then the division is not defined. Remember that from our toolkit we're already familiar with the reciprocal functions, right? Here is f of x equals 1 over x, and here we have f of x equals 1 over x squared. We're now going to be looking at asymptotes. So a vertical asymptote is of a graph is a vertical line x equals a, where the function tends towards positive or negative infinity as the inputs approach a. So we would write that as x goes to a, f of x goes to infinity, or as x goes to a, f of x goes to negative infinity. So vertical asymptote, we're looking at an asymptote like this. And so we can see that we have a vertical asymptote here. Let me actually change colors here so you can see it. We have a vertical asymptote here as our function, so as x approaches 0, and I know that the color is not the best color to see there, but as x approaches 0, our function f of x is going to approach infinity on one end and approaches negative infinity on the other. So we usually write this as x approaches 0 from the positive side, and then we can look at x approaches 0 from the negative side. We have our function goes off into negative infinity. Okay, but there's our vertical asymptote here in the yellow. We have a horizontal asymptote. Let's do like a lime green. Right here is our horizontal asymptote on our y-axis here. And so our horizontal asymptote is going to look like a horizon, right? It's going to be a graph, and it's going to be y equals something. So in this particular case, right, we have a horizontal asymptote here at y equals 0, but we have a vertical asymptote here at x equals 0. Okay. Similarly here, we have a vertical asymptote at x equals 0, but we also have another one here at y equals 0. Because notice how these functions get really, really close to this axis here, but they never touch it. All right. So in both these functions, you know, this is what we just said, vertical asymptote at x equals 0 and y equals 0. So let's sketch the graph of the function 1 over x plus 2 plus 3, then identify the vertical and horizontal asymptotes. All right, so let's go ahead and graph this. So this is going to take the parent function f of x is equal to 1 over x, and we're going to shift it up 3. Excuse me. So we're going to come up 3, and then we are shifting to the left 2. So one way to think about this function is remember that the asymptote starts here. So we're going to shift it up 3, so here's 1, 2, 3. And then we are doing for that horizontal asymptote that was originally here, we are shifting it, because of this plus 2, we are shifting it to the right 2. So we're really going to be here. And so we're graphing this based off of remembering our horizontal and vertical shifts. So our function is going to look like this here and here. So therefore, what's going to be our vertical asymptotes? Our vertical is when we set that denominator equal to 0. So we're going to get x plus 2, we're going to set that equal to 0, and we get x equals negative 2. And so this is our vertical asymptote, right? And we saw that here. We could also see that because of the way that we did the shift there, right? And now our horizontal asymptote right? This was done because of that shift, because we knew that we originally had a horizontal asymptote at 0, so we shifted it up 3 based off of here, so we get that y is equal to 3. Okay, now this is relying solely on understanding the parent function and shifting it, right? So if we don't want to rely on shifting to find vertical asymptotes, right, what else can we do? Well, given a rational function, we can identify vertical asymptotes of its graph. We can factor the numerator and denominator, note any restrictions on the domain of the function, reduce the expression by canceling common factors in the numerator and the denominator. Any values that cause the denominator to be 0 in this simplified form, these are where your vertical asymptotes occur. Note any restrictions in the domain. So when it says no any restrictions in the domain that where the asymptotes do not occur, these are removable discontinuities or holes. So this would be, you know, something that's we're going to be looking at a hole. All right, let's take a look at this example and let's find all the vertical asymptotes of this function. So, you know, this one's a lot more complicated than the one that we just saw. So here we definitely want to be able to factor. So I'm going to go ahead and rewrite this with, just going to rewrite it with that 2x squared in the front. So I have x squared plus x minus 2. So now we want to make sure that we can factor the denominator. We can't really factor that numerator, so that numerator is going to stay the same. But we can factor that denominator, and we get x plus 2, x minus 1. Okay. So we're unable to factor that numerator, so there's no canceling or anything that can occur here. So then because of this, now we set that denominator equal to 0. So when that denominator equals 0 would be when x minus 1 equals 0 and when x plus 2 equals 0. So this tells me that I have x equals negative 2 and x equals 1. These become vertical asymptotes. Okay. So I'm going to have a vertical asymptote at negative 2 and 1. Okay. All right, let's take a look at removable discontinuities for rational functions. So a removable discontinuity occurs in the graph of a rational function at x equals 0 if a is 0 for a factor in the denominator that is common with a factor in the numerator. We factor the numerator and denominator and check for common factors. If we find any, we set the common factors equal to 0 and solve. This is the location of a removable discontinuity. This is true if the multiplicity of the factor is greater than or equal to that in the denominator. If the multiplicity of the factor is greater in the denominator, then there is still an asymptote at that value. So let's take a look what this really means, right? So we're just looking for removable discontinuities, or in other words, we're looking for holes. Okay, in the graph. Okay, so let's take a look here. So we have k of x is equal to x minus 2 over x squared minus 4. So we can go ahead and factor this. So we're going to have x minus 2 on the top. Remember, this is the difference of squares. So this can be rewritten as x minus 2 and x plus 2. And so notice that here now I can go ahead and factor out the x minus 2 and the x minus 2. So I'm left with 1 over x plus 2. Okay. So now I do have a hole, okay, or a removable discontinuity when at x minus 2. And that's because, so I removed it, right? So I removed that x minus 2. So x minus 2, so that's when x equals 2. Okay. So that I know that at x equals 2, I'm going to have a hole. Okay. But now, so this is going to be that removable discontinuity, and now I can graph the 1 over x plus 2, because that's just that parent function being shifted to the left by 2. So I'm going to have a vertical asymptote. My VA is going to be at x plus 2 equals 0, where that denominator equals 0, so x equals negative 2. So here is my vertical asymptote. And so then I know that my function is going to look like this. It's going to go it's going to look something like this. Okay. So I've taken that function 1 over x and I've shifted it to the left 2, and then I have that removable, that whole at x equals 2 there. Alright, oops. Alright. Horizontal asymptotes of rational functions. So a horizontal asymptote of a rational function can be determined by looking at the degrees of the numerator and denominator. So remember that the numerator is on top and the denominator is on bottom. So the degree of the numerator is less than the degree of the denominator, then the horizontal asymptote is y equals 0. The degree of the numerator is greater than the degree of the denominator by 1, no horizontal asymptote. But there's a slant asymptote. So the degree of numerator is equal to the degree of the denominator, horizontal asymptote at ratio of leading coefficients. So we'll take a look at what this means, right? So really, this is one way to kind of remember it. A function could potentially cross only a horizontal asymptote. So degree n is less than the degree of d, so our numerator is less than the degree of the denominator. We have an asymptote at y equals 0. If the degree n is greater than the degree d by 1 only, so then that's an example of that would be, you know, if I have x cubed on the top and I have x squared on the bottom. So the numerator, x is bigger than the denominator, but it's only by 1. We have a slant asymptote, right? So we're going to be using synthetic division to figure that out. And if the degree of the numerator is equal to the degree of the denominator, the asymptote is a fraction of the leading coefficients. So let's take a look at some examples here. I know it keeps zooming in. There we go. Identify the horizontal or slant asymptotes for the following functions. So for A, we're going to take a look, right? So what do I have here? If I look at the 3 options, I look at the degree of the top, I have a 3. Degree of the bottom, I have a 3. So in this case, I'm in case 3, right? Because the degree of n is equal to the degree of the denominator. So I know that the asymptote is a fraction of the leading coefficients, right? So that means that my horizontal asymptote is going to be y equals, and then it's a fraction of the coefficients, so 6 over 2. Okay, well 6 over 2 is just comes down to 3. So this tells me that my horizontal asymptote is y equals 3. Okay, so it's again, it's just the leading coefficients. Let's look at B. Alright, so here my numerator is greater than my denominator. So I have that the degree of the numerator is going to be greater than the degree of the denominator. Okay, and if we look back up here, right, that's going to be case 2. Okay, and it's greater by 1. So because it's greater by 1, we're going to be looking at a slant asymptote. Alright, so the way that we figure this out is we're going to do synthetic division. So we're going to have x plus 2, you know, and so this is really a division problem, right? It's the numerator being divided by the denominator. So we're going to have x plus 2 equals to 0, so x equals negative 2, so it's going to be negative 2. And then we're going to have the coefficients of the numerator. So here's 1, negative 4, and 1. Negative 2 times 1 gives me a negative 2. Negative 4 and negative 2, that gives me a negative 6. Negative 2 and negative 6, this gives me a positive 12. And then 12 plus 1 gives me 13. Okay, so this here, this is our remainder. But we're going to ignore the remainder, and we're just going to focus on our quotient. So our quotient here, right, remember this was degree 2, so this would be degree 1, so it's going to be x minus 6. And so y equals x minus 6, this becomes our slant asymptote. Okay. So again, we did synthetic division, and we got our slant asymptote from that division. Okay. All right, let's take a look at C. Here I have the degree of the numerator is less than the degree of the denominator. So this would be our case 1. Right, so if you remember going back all the way up to case 1, over here, this tells us that our asymptote is equal to y equals 0. So we can look at this and say, all right, well, my horizontal asymptote here is going to be y equals 0. Okay. All right, let's take a look at how to graph this function. All right, so when we go ahead and graph this, there's a couple of things we want to take a note. First, let's start off with our vertical asymptotes. Our vertical asymptotes, remember, are going to be our denominators. So we have x plus 1 squared times x minus 2 squared. Sorry, no square there. All right, so then in doing this, we're going to set this equal to 0. So we can see that we end up with x plus 1 squared equals 0 and x minus 2 equals 0. So here we have x equals 2, and then here we're going to end up with x plus 1, because that square, you know, it's just taking the square root of both sides, but the square root of 0 is just still 0. So then we have x equals negative 1. So now, because this 2 is here, let's change colors. Because of this 2 here, right, that means that this, right, has a multiplicity of 2. So let's come over here and let's go ahead and start plotting these. So we have a vertical asymptote at x equals negative 1. So here's my asymptote. And then we have one at x equals 2. Here's my other asymptote. All right, let's keep in mind this continuity. Now let's take a look at our horizontal asymptotes. So now for our horizontal asymptotes, let's check out the degree. So the degree of the numerator is going to be this x times this x, which is going to give me an x squared. Here I have this x is going to be squared once I play with that, right? Because this is going to be x plus 1 times x plus 1 times x minus 2. So once I multiply this out, I hope everybody can see that I'm going to end up with an x cubed. So I'm going to have a degree. So in my numerator, my degree is 2. In my denominator, my degree is 3. So I do have that the numerator is less than the denominator. So this tells me, because the degree of the numerator is less than the degree of the denominator, we're back to that case 1. Right, which means that I have a horizontal asymptote at y equals 0. Okay. All right. So let's come over here at y equals 0. All right, there we go. So now let's go ahead and figure out, okay, well, what happens? Do I have any y or x intercepts, right? So remember, so for a y-intercept, we're going to go ahead and set x equal to 0. And so when I do that in this function, we're going to get f of x is equal to, let me write down the, so I have x plus 2, x minus 3, all over x plus 1, x minus 2 squared. All right, so let's plug in 0. So I'm going to get 0 plus 2, 0 minus 3, 0 plus 1, and squared, and then 0 minus 2. So we're going to get 2 times negative 3 times 1 squared, which is still 1, times negative 2. So we're going to get negative 6 over negative 2, which is 3. So our y-intercept is going to be 0, 3. So let's go ahead and plug that value in. Okay, now do we have any x-intercepts? Right. So in order for us to have x-intercepts, that means that we would set y equal to 0. So if we have f of x, let's write this equation again. So I'm going to have x plus 2 times x minus 3 all over x plus 1 squared x minus 2. All right, so in order for this to equal 0, right, that means that, because I'm going to set my y equal to 0, my f of y equals 0, the only way I can get this to equal 0 is if my numerator equals 0. So I would have x plus 2 times x minus 3 equals 0. So when does this happen? This happens when x equals negative 2 and when x equals 3. So this means, let's come back over here and plot our x-intercepts. So we're going to be at negative 2 and 3. Now both of these x-intercepts have multiplicity 1. Right? So that means that it's gonna go through, right? So it's gonna cross the x-axis. Okay, so we're gonna cross the x-axis there, and then we're gonna tend towards the asymptote. We don't have any crossing of the graph in the middle, and so this is what we're with. Let's see if we can find anything else here. We have our x-y intercepts. We have our asymptotes, one vertical asymptote with a multiplicity of 2. So what happens, let's talk about the multiplicities here. When I have a multiplicity of 2 with an asymptote, that means that as the asymptote, if this is my asymptote, if it's an even multiplicity, my function is going to face the same way. If it's an odd multiplicity, like in this case over here, then my functions are going to go in opposite directions on that side of the asymptote. Okay, so that's important because when I look at this graph, now that we start to sketch this out, I know that because 2 is an odd multiplicity and I'm already up here, since I'm here in the middle, this means that this is going to have to kind of travel this way. So let's go ahead and sketch it. So we're traveling this way, which means because this is a non-multiplicity, the function here has to travel this way. So we're going in opposite directions because of the odd multiplicity there. But because I cross the x-axis, that means that this function is going to come this way and it's going to start trending towards the asymptote. Now on the other side, so here's my function. I'm going to go through my y-intercept. Right now here I have an even multiplicity, which means, so if I come back up this way, right, because I'm not crossing that x-axis in the middle, that means that because this is an even multiplicity, that this function looks like this here. And now this is going to kind of dip underneath, but then it's going to trend towards that asymptote again. Okay, so again, that's because of the even multiplicity here with this asymptote versus that odd multiplicity here with the asymptote. Okay, all right, that's that example.